We are continuing our series on within subjects designs. In this series, we're primarily focusing on repeated measures and the randomized block design. We just concluded that we could make an omnibus inference about inequality of means beyond our sample data to a larger population. Now let's focus on multiple comparisons, in which we may either want to follow up the omnibus or in some cases skip the omnibus analysis and focus more on specific comparisons. As I've said in past video series, there are many multiple comparison procedures, probably approaching 100, but we're just focusing on 3 of the most common ones, and I'm doing the same 3 in this series. Tukey's method, which we would use if we want to look at all pairs of differences. Bonferroni's method, if we want to plan our comparisons in advance and focus on a smaller subset of comparisons. Or Chaffee's method, if we want to do true post hoc analysis. That is, if we want to follow up the omnibus by fishing around for the largest differences we can find and creating confidence intervals for those differences. What we are going to find is that creating these confidence intervals is facilitated by setting up our analysis as though we were working between subjects instead of within subjects. I'll show you what we mean as we go along. Let's go ahead and take on this analysis. So to get the Tukey confidence intervals, we're going to run the ANOVA again as if it had been a between subject study, but without interaction. Now in this particular line 139 right here, I'm going to avoid having to put the $sign for every variable by using a data statement that we can use to indicate the data that we want to apply for all these variables. And that is going to be the long data. This is the sprint data in the long format. Let's go ahead and look at these results after we get a summary of them. We're going to run the AOV, store the results, and then get a summary of those results. Of particular note is that I'm putting in both trial and ID. Remember, in the long format, we set those up as factors, but I'm not putting in an interaction. You do not want to put in an interaction when you are using this kind of design. So let me go ahead and run this, and let's look at this table. Now, you should see some things that you can equate to the previous table that we created. This is a between subjects table, but here we actually had a between subjects residual right here, and we had a within subjects portion of the ANOVA table right there. That between subjects and within subject is separated as it should be. So this ANOVA table up here is actually the correct ANOVA table. This is not really correct. I'm just fooling R to help me create my confidence intervals. Why is this not correct? This is treating trial and ID as if they're both between subjects factors, and we know that's not true. So the ID that you see right here, in which it's actually using it as a factor and creating an F statistic and an F probability, you can't actually do that here. This ID is what is separated out as the residual that we're taking out up here. Look at the sums of squares. Look at the degrees of freedom. 6 degrees of freedom, 1.9374. 6 degrees of freedom, 1.9374. So really this piece should not be in our ANOVA table. However, because it has been taken out of the residual, even though it's falsely identifying it as a testable factor, it has been taken out of the residual so that our residual is correct. Our residual here is the same as it is here. So if I know what I'm doing, I actually could have used this table and I would not have had to get a projection. I would not have to use that projection function in order to get my residuals. I mentioned when I did that, there's another way of getting the residuals that may be easier to understand, and this is it. I could get the residuals right from this particular table here. After running this, I could actually get my individual residuals in order to be able to look at my QQ plot, and I could have done that. Why didn't I do it? Because this is not actually right. This is a little bit of trickery going on. This, again, should be a separate residual. It should not be part of this ANOVA table, making it look as though it's a testable factor. So I'm going to ignore that. I literally am going to ignore that. Can I go ahead and do these contrast with this table? I can, because I can ignore that ID. And in fact, if you look at the Tukey command here, I'm putting in the Tukey HSD and I'm saying which equals trial. In other words, I want you to use that trial and I want you to use those residuals, but I don't want you to use this ID. So that is exactly what we want to do, because that ID should be back up here as a separate residual. I want to use this table, and that's what I'm doing by saying which equals trial. Now, if you think about when we did the sphericity check, we had 15 differences, and the same is true here. So I don't know if Tukey is really what you're going to want to use if you have this many repeated measures. If we had 3 repeated measures, like a pre, post, and follow-up, then you would have 3 times 2, or 6 divided by 2 is 3 differences. And those 3 differences, that might make sense to do Tukey. Even if we only had 4 trials, 1, 2, 3, and 4. 4 times 3 is 12, divided by 2 is 6. You'd have 6 differences. That might be okay. But to have 15 and really truly be interested in all of them, I'm not so sure. And with all multiple comparison procedures, using Tukey as well, the more comparisons you're doing, the wider those confidence intervals are going to be. So if we do all of these, I look and I can see indeed some differences here that are true differences, but I also notice that I have pretty wide intervals. Look at that first one, from 0.02 to 0.47. Well, you might say that's not so wide, except remember what we're dealing with in terms of our differences way back here. We're talking about only about a half of a point between the longest time, or a half a second between the longest time and the shortest time. So that actually is a fairly wide interval, but nonetheless, there they are. This P adjustment column has some meaning to it that I don't want to get into because you don't need it if you're focusing on the confidence intervals. Here is the actual difference, and then here is the confidence interval for the difference that I'm interested in between 1 and 2 outside of this study. So I have 15 confidence intervals for 15 differences. I am 95% confident in the entire set all at once. It's not 95% confidence in any one interval, it's 95% in the entire set. How do I know that? Because I happen to know that 0.05 is the default type 1 error rate for the Tukey HSD function, as it is for most of the functions that you use that involve inference in R. If we want to make inferences based on looking at the data, we could use Chaffee. For example, if you look back again at this graph, the largest difference is between trial 1 and trial 5. Suppose I actually look at the data and then say, I want to make a confidence interval for that largest difference. Well, then you have no choice but to use Chaffee, because now you're going on a fishing expedition. So we must use Chaffee. This is not a planned comparison. This is a pure post hoc comparison. So here's my contrast. It's the difference between 1 and 5. Here's the standard error of the contrast. If you watch previous videos, you'll see how I determine the standard error. I'll briefly remind you that for that standard error, I get the mean square residual from my ANOVA table right there, or going to the real correct ANOVA table right there, same thing, 0.01895. And so I put that in here for my mean square error or mean square residual. And then I put in my weights squared over the number that goes into a mean. How many runners, those sprinters, how many were actually in each trial? It was 7. So I'm comparing the first trial with 7 sprinters to the second trial with 7 sprinters. That will give me the standard error of the contrast when I take the square root. For Chaffee's critical value, we take the degrees of freedom in the numerator of the F we're interested in, and that is this one, that is trial. So the degrees of freedom for trial is 5. The degrees of freedom for residual is 30. So I take the numerator, 5, times getting a quantile on the F distribution out at 0.95 with, again, 5 and 30 degrees of freedom. Multiplying standard error of contrast by critical value gives me μ, and then adding and subtracting μ from the contrast gives me my interval, and there's my interval from 0.22 or 0.23 to 0.75. So that means that from trial 1 to trial 5, I can infer a drop in time somewhere between about 1/4 of a second and 3/4 of a second. Let's compare that to what we got with Tukey. What we got with Tukey is from between 0.27 and 0.72 for that same interval. Well, think about that. That's narrower. Tukey's was narrower. You might say, well, but we only did one interval here. What gives? Remember that Chaffee allows you to do as many intervals as you want. So even though you only did one, you could have done 100. Chaffee doesn't care. Chaffee is post hoc. Tukey, on the other hand, Tukey allowed us to get a narrower interval because it only does all pairs, and it is the most powerful for all pairs. Now, with this many repeated measures, if we don't go on a fishing expedition, but if we're thoughtful ahead of time, we could do Bonferroni. That is, we could then look at adjustment only for looking at pairs we're interested in. There's another advantage to Bonferroni. We don't have to consider homogeneity of variance. That is, we don't have to worry about the sphericity assumption. Now, if you're not going to worry about the sphericity assumption, you're going to skip the omnibus test. If you do the omnibus test because you did meet sphericity and you're still doing Bonferroni, you only go on to Bonferroni if you reject the omnibus test. But you could skip it entirely and do a planned comparison. So, for example, I might want to say, I'm going to be interested in the difference between trials 1 and 2 because that tells me something about the practice effect. Or I might say, I want to be interested in the difference between trials 1 and 6, my first trial and my last trial. Or maybe I want to be interested in between trial 2 and 6, how much change there is, because I assume that after one practice, I've kind of got the runners hitting their stride, and then I want to see what kind of fatigue there is after trial 6. I'm just making up this sort of theoretical anticipation, but that's the way you do it. You think in terms of what makes sense to me and what am I interested in. So in this case, I'm doing 3 t-tests. I'm doing it between trial 1 and 2, and notice I have to say paired equals true because these are the same individuals. So these are actually one sample t-tests, 3 one sample t-tests, looking at the difference scores between 1 and 2, the difference between 1 and 6, and the difference between 2 and 6. And if I look at these intervals are, let's take a look at the difference between 1 and 6 here. It's from negative 0.04 to 0.67. That means that, and again, it's based on the way that we subtracted here. So here it was 6 minus 1, and 6 was a smaller number because it was faster. And so the decrease in time from 1 to 6 in the population is going to be between about 0.04 seconds and 0.68 seconds. Let's compare that one to Tukey. This is 0.06 to, down here, 0.04 to 0.68. That's 1 versus 6. That is 1 versus 6. So I'll go back up here to 1 versus 6, and I have here between 0.13 and 0.58. 0.13 and 0.58, whereas down here I ended up within 0.04 and 0.67. So again, Tukey gave us the narrower intervals. Tukey is powerful for pairwise comparisons, and that might be a little bit surprising here because we only did we only adjusted here based upon 3 contrast, but that indeed is the way it turned out there. Also, it isn't exactly the same variance in both conditions. And the other thing that's going on here is that this is not assuming equal variances, and Tukey's is. So this one is really based upon the 2 groups only, whereas Tukey is based upon this residual here that comes from all groups, which is a better estimate of variance if the variances are all equal. And we don't think that they're probably exactly equal. They were just not dissimilar enough for us to discount the condition for valid inference. So those are the 3 methods. We have the Tukey, we have the Chaffee, and we had here the Bonferroni. Each of those have advantages and disadvantages. Tukey, most powerful for all pairs. Chaffee allows you to go fishing. Bonferroni does not require sphericity, and often with fewer numbers of pairs can give you more power, even though in this case, when we looked at those 3 pairs, at least the one I focused on here, it did not give me more power. So that brings us to everything except me taking on a challenge and doing a report, and I will take that on in the next video.